Okay, folks, here we are with our continuation of general review. Skipping a bunch of things in the review packet. I am going to be checking off the things we work on, but I am going to do this on purpose so I cover the things I think are going to be most important for this particular test, and we might come back later on and hit on some other things as we go on there. So the next thing we're going to talk about really quickly is continuity. The definition of continuity. Remember, continuity just means connected. If a function is connected on all parts, it is continuous. So let me just take this page off for a second. I'll come right back. Real quick picture. Let's make sure we're in the right view. There we go. We have a function that's drawn right here. Pretty much, if you have a regular, smooth, continuous function, all the points are continuous. They're connected. At certain points, they are not continuous. Here is one example where it is discontinuous. Here's another example. And I've left out the third type. I should put this on here right here. Whoop. These are the three types of discontinuity. They are infinite. I should have just wrote on the packet, shouldn't I? I'll remember that next time. They are infinite. Why don't I pause this and fix that? Hold on. And look at that, skadoosh, just like that. We have three discontinuities on this picture. Here, here, and here. Those discontinuities are known as removable, step, and infinite. And if you look on the last page, the definition of a limit, sorry, definition of continuous is that the limit from the left equals the limit from the right equals the actual value of the particular function. Okay? For this function right here, removable is the only type where the limit from the left equals the limit from the right. I know what you're thinking. That's not true on infinite. The limit, there is actually no limit, but it is heading towards infinity. Equals the limit from the right. But the value is not the same there. Don't confuse continuity, which just means connected, with differentiability, which also means smooth. There's one type of point that is continuous but not differentiable. You should see it on the graph right here. It is, just grab a different color. Let's go with green. How do I use green? Let's go with orange. Right here is, it is continuous but not differentiable. Meaning there's no derivative at that particular spot. All these other spots have derivatives. There's little tangent lines that show you the slope. There is no one I could perfectly fit on here. That's why it doesn't have it. So from a mathematical standpoint, all they're going to ask us about continuity is how do we know, first of all, they ask us how do we know something is continuous or is not continuous. We're literally just going to state the definition of continuity. We're either going to say this is true or this is not true. So why is it discontinuous at point A right here? Because the limit as x approaches c equals the limit as x approaches c from the positive direction does not equal the value. How do we know at point B here it's discontinuous? Because the limit as we approach c from the left does not equal. We'll change that to the limit from the right. And for infinite discontinuity, we could put it could just say that it's not equal to the value at the piece right there. There is no value as we're going on there. Algebraically, I don't know if they're going to ask us this algebraically because I don't know if they can, but this is the approach that it's going to take. They will give us a function and say, make it continuous. And all we're going to do that means we have to solve for k. We have to set the limit from the left equal to the limit from the right equal to the value. And all we do is we plug those numbers on in. So if I plug 2 into here, this is the value I'm looking to plug in. I plug in, I get 4 plus 6. I get 2 times k. And I get 4 plus 6 again. When you do this, you'll always get one thing that repeats. You can just get rid of that because it's already there. and I solved for k. So the value that makes that continuous is k. You can then put it in your grapher and see continuous. The big piece about continuity is it's going to evolve, though. I think it's just going to be knowing this definition. Limit from the left equals limit from the right equals the value. Okay, moving on. Once again, really quickly, we're going to talk about differentiability. And the big word that's on here is the word smooth. There it is. The definition of something being differentiable is the same of it being continuous, except instead of using the actual values, it's going to use the definitions of the derivatives. So the derivative from the left equals the derivative from the right equals the actual derivative at that point. It just says that the tangent lines, as they move into place from one side, will also connect on the other side, but will also connect smoothly. So if it's smooth, it's differentiable. When the values from the left match the values from the right, like so. But the slopes on the left, which are positive, and the slopes on the right, which are negative, don't approach each other, don't head toward the same thing, we will get something that's not differentiable, and it is going to be a cusp, just as listed right here, down on the picture. I think we're going to have be enough with just this information right here. Basically, if something is differentiable, if you already know it's smooth, then it has to be continuous. But if it's not continuous, then it can't be differentiable. So, for example, if I drew this picture, I'll do it right here. I'll draw a function that's not continuous. At A, I know this function is not continuous, so I know it has to be not differentiable at A, which makes sense. If it's not continuous, it can't be smooth. If a function is already smooth at A, then we know it's already continuous. One thing implies the other. I think that's about all they're going to have on that right there. I'm going to skip over the theorems for right now. We'll talk about those at a later on point. They're used to prove things, but we'll worry about those at another point in time. So let's just talk about differentiation, our last topic for today. And differentiation is just taking derivatives. That's all it is. Differentiation is derivatives. It means instantaneous slope. It means slope at a point. Okay? Now the big thing is, the big difference between average slope, which is fib-faba, you can see ever, and instantaneous slope is average slope uses 2 points, and instantaneous slope uses 1 point. We can use average slope to estimate instantaneous slope. And you're going to see this is going to be here a lot. It's just going to say estimate the instantaneous slope using average slope. It just means we're going to use 2 points instead of 1. I'm going to show you an example of that coming up. I talked about this one here a little bit yesterday. I'm not really going to worry about it. This is the formal definition of a derivative. It really just comes from fib-faba, where I take the 2 points and I start making them really close together. So these ones are pretty close, so they'll give me an average slope. But instead of making them really close together, I'm going to make them exact. Let's not worry about that right now. Let's just focus on differentiation. Differentiation is instantaneous slope. Slope at 1 point. We can estimate it with average slope. And we have all of our rules for taking derivatives. Now, like I said, because we're going to be have our calculator, mastery of the rules isn't going to be, I don't think, like the key to the test right now. But pretty much we're good at taking derivatives. We practiced some of them yesterday. Remember, k is just a constant. Derivative of any constant is 0. We're taking away an x as we go. A to the x is a. X to the n is n, x to the n minus 1. I hate it when it's written like that. We just know if we're taking the derivative of x to the 100th, that's 100x to the 99th. These two aren't really rules. They're just saying if you have two separate pieces, take the derivative separately. Then we have the, who wrote power rule? Oof. Dollar. Fix it in your book. That's the product rule. It's the quotient rule. And it is the chain rule, which is right here, UV. I'm going to come over to the other side for a second. This one comes up a lot because they know it kind of messes people up a little teeny bit. They'll say the sine of 3x, and ask you to take the derivative of that. So the derivative of sine of something is the cosine of something, times the derivative of the inside, which is 3. When they write it down, they're not going to write it like this. They're going to rewrite it as 3 cosine 3x. And then they may ask you to take that derivative again. 3 cosine 3x. I'll keep my parentheses for a minute. Derivative of that is the 3 that's already there. Sorry. Okay. Derivative of cosine of something is negative sine of something. Times the derivative of the inside again is 3, which would end up being negative 9 sine of 3x. You can see as we keep taking derivatives like this one right here, it's going to keep going up by factors of 3 and negative 3 based on the problem that we have right there. Flipping to the other page. There we go. We have our other general rules, which are there's our chain rule, just written kind of weird. Derivative of the outside times derivative of the inside. We love e to the x. Derivative of e to the x is e to the x. This is the one no one remembers. Derivative of n to the x, or derivative of 2 to the x, is the same as itself times the ln of 2. All exponentials have themselves as a derivative times the ln of their base. The reason there's nothing up here is because the ln of e is 1, and that's why it's gone right there. And the derivative of line ln of x, line, is going to be 1 over x, as we have right there. So I'm going to turn the page. I've got the trig rules on the next page. One more things right here. Remember, take derivatives of cofunctions. A minus sign appears on there. There's Coco cried. So remember that tangents seek secants, and secants seek tangents. The cofunctions are exactly the same, just with the word co on it and a minus sign on there. And then there are our 6 ticks and your dead problem, which we will review as we get closer. But like I said, I don't think we have to worry about it, because I think we're going to have them in front of us. These are listed here. Inverse cosine, inverse cosecant, inverse cotangent. They're just negatives of the one above them. But what I'm letting you know is you're probably not going to see these. I'm going to put a slight slasher there. You can pretty much work with these 3 as we go right there. So really quick again, I just taught, and this is a little bit of touching on some of the same things. I really quickly talked about the chain rule. It's going to be there a bunch in terms of, not this particular piece right here. That one's not really going to be there, but this version of it is going to be there. We do the derivative of the outside and multiply it by the derivative of the inside. So the last non-question part, oh, I lied to you, 2 more parts. This we just before. Differentiability implies continuity. If something is differentiable, then it has to be continuous. So if you look along here at the values I've gone for, this one's not continuous, so it's not differentiable. Oop, got it, Lane. Move it up. Not continuous, not differentiable. Not continuous, not differentiable. Here, it's very different. This is all smooth, so it's continuous everywhere. Look at this graph over here. Oop. Look at this graph over here. All smooth, so it's all differentiable, so it's all continuous. These have 2 spots where they are continuous and not differentiable, because those are cusps. Last part of the video without problems, I'll do a separate video with problems we're going to work on, is you will see that the AP is going to ask you over and over and over to estimate derivatives using the closest 2 points, which would be fib-faba. It's going to happen a lot. We have to make sure we use the appropriate symbol here. So, for example, they're going to give us tables of values right here. And they're going to say estimate the derivative at 2. So that means find or estimate f prime of 2. So on this graph, I have to pick the 2 points that are closest to the x value of 2. I could use either these 2 points or the next 2 points along the line, or to give me an estimate. I could also use the points around it. It doesn't matter which ones you use, but the important thing is how we write this out. So f prime of 2, I'm not going to write anything in there yet, would be fib-faba. Okay, so it would be 2 minus 1 with 5 minus 3 on the top. I don't have to simplify the math. I can leave it like that, but Cal gets mad if I don't. So I'll go 2 over 1, and we've got our answer right there. But the big thing is, if you put an equal sign here, that's where they're going to take off points for. It has to be approximately. The instantaneous slope is approximately 2, because I estimated it from the table up over there. I could have also done 3 minus 2 over 7 minus 5. That would work as well. I also could have done 3 minus 1 over 7 minus 3 and use the points on opposite sides of it, but I couldn't use 3 and 4 and 2 and 4, they're too far away. And just remember, estimating slope from the graph is pretty straightforward. A slope of 0 has no angle to it. A slope of 45 degrees down is -1. A slope of 45 degrees up is +1, and a straight up and down is approximately infinity. I estimated this slope at -4 just because it looks like it's really, really slopey right there. Those are all just estimates as we go. Okay, we have gone up to this part right here. This is on page 13. That's your first video. Your next video is going to be coming. It's going to contain problems from the review packet, which the ones you're going to work on over tomorrow. Take care.